we have written down the continuity equation in its different forms: general form, the steady form, steady incompressible form, or for compressible flows. Now we see how this continuity equation can be applied to simple flows, and from simple flows we can move on to difficult or complicated flows as well. But for the sake of demonstration, how do we apply these equations and how we use these equations are different in its different manifestations. We discuss here some examples. Of course, it is not possible to discuss all possible examples in a standard course, but we discuss some of the examples whereby this equation is utilized and applied. So here is a question in which we apply this equation to determine different aspects of fluid flow as far as mass conservation is concerned. The question is that a two-dimensional converging duct is being designed. So this is about designing a wind tunnel and a duct from which fluid will be flowing from one step to another step, and they want to determine that how the fluid will behave, how its functionalities, the velocities, the density, etc. will change. And if we know it for a hypothetical case, then we can apply on real cases also. For example, when we want to determine the drag coefficients or other things that are related to designing of, let us say, vehicles or other products. So a two-dimensional converging duct is being designed for a high-speed wind tunnel. The bottom wall of the duct is to be flat and horizontal. So this is a given condition. And the top wall is designed to be in a curved manner such that the axial wind speed U approximately increases linearly from the U1 equals 100 meters per second at section 1, that is at the beginning, and it increases to the speed of U, what we call as U2 equal to 300 meters per second at section 2. We show it in a diagram shortly. Meanwhile, the air density rho is to decrease approximately, again linearly, and this is an approximation, not exact, but quite a good approximation in most cases. From rho 1, originally it is 1.2 kilogram per meter cube at section 1, and it decreases to rho 2 equals to 0.85 kilogram per meter cube. So you can see it is reducing from 1.2 kilogram per meter cube to 0.85 kilogram per meter cube at section 2, that is at the end of the duct that is being designed. The converging duct is kept at 2 meter length, and it is also 2 meter high at section 1. What we want to know is, we want to be able to predict the y component of the velocity v that depends on x and y in the duct. We want to plot the approximate shape of the duct, ignoring the friction on the walls, and how high should the duct be at section 2, that is at the exit of the duct. So there are several conditions that have been imposed, several assumptions that have been imposed, and so we have to consider all of them, and by considering those assumptions, those given conditions, we have to determine the three things that are required here. That is the y component of the velocity v, plotting of the shape of the duct, and also considering how high the height of the duct at exit. For given velocity component u and density rho, remember these things are given to us, we are to predict the velocity component v, plot an approximate shape of the duct, and predict its height at the exit. So if we draw a rough diagram, it looks like this. For the design of this converging duct, converging means initially it has a higher inlet, but at exit it has been reduced. So it is converging in a way. And therefore initially the height is 2 meter and it's 2 meter long also. That is also given, that this is 2 meter and again the height is also 2 meter, and the wind or the fluid is moving, or of course it is air, is moving from left to right as shown by the arrows. So it's a converging duct designed for a high speed wind tunnel, and this rough diagram that has been shown is not exact diagram. Therefore this remark that it is not to scale. So assumptions are, as we have said it before, but we consider them again, that the flow is steady and two-dimensional in XY plane. The friction on the wall is ignored. So no viscosity, no friction, no drag. So therefore no heat generation, no dissipation of energy and that kind of consideration. So friction is ignored and the axial velocity u increases linearly with x and the density rho decreases linearly with x. So these are again the given conditions to us. Rho is supposed to be decreasing linearly with x from initially it has a higher value but it decreases slowly, while the velocity increases from its initial position to the place where it exits the duct. The properties also, standard properties also have to be kept in mind while looking at the solution, and that is the fluid motion, which is and the fluid is air, of course, wind is air, all this is being done at temperature of 25 degrees centigrade. The speed of the sound is about 346 meters per second. So the flow is subsonic. We call it subsonic because at that speed of sound, Mach number is less than equal to 1. But it's compressible because rho is changing. Rho is decreasing linearly from the point 1 to point 2.